In this video, I want to consider how we determine the direction of groundwater flow from a contour map of either the piezometric surface for a confined aquifer or a contour map of the water table for an unconfined aquifer. So this is a map view here where I'm showing two contours of head. These are 60 units above datum. Let's call it feet, 60 feet above datum and 50 feet above datum. So we know in general that the water is going to be flowing from high head to low head, but what exactly is the direction that water is going to be flowing, the groundwater is going to be flowing? So let's start by picking a point in the middle here. And we want to know, so water is somehow going to be flowing through this point, and we want to know what is the actual direction that the water is going to flow. So right here, let's say that the head is about at 55 feet above datum, and we want to know what direction is it going to go. Now we know it's got to go from high head to low head. It's at 55 feet, but we could go from high head to low head at any number of directions. All of these are going from 55 feet towards that 50-foot contour, so head is decreasing along all of these lines, and the question is, well, which is the correct direction of groundwater flow? And to figure that out, we need to think about what we mean, what Darcy's law says. So I'm going to write Darcy's law here. It says that the groundwater flow, we'll just call it the specific discharge here, and remember that's a vector. We're not going to worry about computing it. We're just going to look at the direction, is equal to minus K, the hydraulic conductivity, times the gradient of the head. And the gradient of the head, remember, is the change in the head value divided by the distance between the 2 points. So in our case here, the change in the head, so actually, I'm going to back up a second here. The gradient is defined as the slope, change in head divided by change in distance. That gives us the maximum change, the most rapid change in head in a given direction. So what we want to do actually is we want to maximize this slope delta H over delta S. We want to maximize it. Well, what do we know? We know that delta H is going to be the change in head, which if we're going from this blue dot to the line is 5 feet. So this is going to maximize 5 feet over the distance delta S. And remember what I mean by that distance. If I'm going in this direction here like this, then this would be delta S. And whatever that distance is, the slope would be 5 feet divided by that distance. And I think you know what the answer should be. If we want to maximize this number, it's going to be maximized when the denominator delta S is minimized, right? So when this thing is as small as possible, then the fraction will be as large as possible. The slope will be as large as possible. And you probably know that the way to get the minimum distance between this point and the line of 50-foot contour is to take the direct route which intersects the line at a right angle. So the shortest distance from a point to a line is a line that meets the line in a perpendicular 90-degree fashion. So this pink line here will be the shortest route that will get us from that point to the line, and therefore that will be, actually we should probably actually have put a minus sign in here. Sorry about that. We're actually talking about the minus sign here. So what we were actually determining was the direction of the gradient. Remember, the gradient actually would be in this direction like this. It's the direction in which the head is increasing most rapidly. Groundwater flows in the exact opposite direction. So groundwater is going to flow in the direction directly opposite the direction in which the head increases most rapidly, and that will be in this direction. But once again, the main point I want to conclude here is that the flow of groundwater is going to go in a path that meets these contours at a right angle. That's the key point. The groundwater flow paths on a contour map of the piezometric surface or the water table are going to meet the contour lines at a right angle. So let's demonstrate how this works. Here's another contour map I'm showing now, a bunch of different contours of head, either again a piezometric surface map for a confined aquifer or a water table map for an unconfined aquifer. And let's say we want to sketch the path of groundwater that emanates from this blue point here. So we're going to go, remember the rules we're going to apply are we're going to go from high head to low head, we're going to cross the contours at a right angle, and in addition we're going to try to draw a smooth line. We don't want jagged, abrupt changes. So this takes some practice here, but so if we're starting from this point, high head to low head is going to take us from left to right, and we're going to sort of go in this direction like here. We're going to try to cross this line. There we go. It's something that wasn't great. Get a little better at this if we practice here. There we go. We're going to cross it at a right angle. And as we continue in this direction, we're actually going to have to curve our path so that we now cross the next two contour lines at a right angle, and keep curving it. There we go. So this is my groundwater flow path, high head to low head, smooth line, crossing each of the contours at a right angle. Now let me make one more point that is a common mistake that students sometimes make. When we draw this path, I guess we should have implied that this is a path that went through that point, but presumably it started before that point. It got to that point by flowing from distances further up gradient, right? It would have followed the path sort of shown in dash there. Point I want to make is that when you're doing this exercise, you need to both look forward and back. So if we're starting at this second point given by the green dot here, it's incorrect to simply go, okay, we're going to go sort of like this, okay? That's not right, okay? And the reason is that if I sort of extend this back smoothly through that point, I am not going to cross the previous upper contour at a right angle. So what we need to do in this case is actually think about what happens before we get to our point. So if before we get to our point, we would have flown, the groundwater would have sort of flown in this direction like this. So now we can continue through our point here. And I'm doing a terrible job because it's a tablet, but you get the idea. It's going to cross that by a right angle, and then we're going to have to kind of curve right through the 70 and the 60, and we're going to eventually come out like this, something like that. All right, so there is how you calculate or how to draw the flow paths for groundwater on a contour map of either the piezometric surface for a confined aquifer or of the water table for an unconfined aquifer.